Good afternoon, folks. How are you today? We are in our last lab, lab number 14. Before we begin, again, I want to remind you, if you have not already, please log in at smartevals.com and fill out the course evaluation. So our problem today is about heat dissipation by a radiating fin in space. So imagine that we have a long fin radiating out in space, and space is at 0 degrees K, absolute zero. Now, in Fahrenheit scale, our absolute scale is called 0 degrees Rankine. So, if this fin is attached to a hot body, and let's say that hot body is at a temperature of 2000 degrees Rankine, then what will happen is this particular fin is going to radiate out heat, and our temperature profile would look something like this. So at this end of the fin, temperature is 2000 degrees Rankine. At the other end, it is 0 degrees Rankine. So what we do is we model this using a differential equation. So if you have taken a decent physics course, or if you are taking a heat transfer course, you'll find out that your second derivative of temperature with respect to position. So let's say our x-axis starts here. In general, this could be a function of x, t, and remember the first derivative, dt dx. It turns out that it is a very simple differential equations. There are a bunch of constants, which we'll call capital K, and these constants are things such as a Stefan Boltzmann constant. This is like a universal constant. It depends on emissivity of the fin, the thickness of the fin, the thermal conductivity of the fin. So we can put all of these together as a capital K. They are constant for a given problem times temperature to the power 4 minus whatever is the temperature of the space T0 to the power 4. So notice this is a non-linear, even though it looks very simple, it's a non-linear differential equation because our second derivative is non-linear with respect to t. So therefore, analytical solutions are not available. So we have a second order differential equation, and we have two boundary conditions. We say at x is equal to 0, temperature is 2000, and at x is equal to L, temperature is 0 in Rankine. So remember our degrees Rankine is degrees Fahrenheit plus 460. Just like we say degrees K is degrees C plus 273. Okay. So anyway, we have a boundary condition, second boundary value problem. We have two boundary conditions. So what we are going to do is our guess is going to be the gradient. So at x is equal to 0, we are going to guess what is dt dx in order to match the boundary condition. So this is going to be our match. Now we have to be very careful here. What will happen is, let's suppose we are guessing our gradient. So if we guess it too steep here, what will happen is we'll start solving the differential equation and we will fall below 0 degrees K and our equation is going to blow up. Let's say if we guess our slope to be too shallow, Then we'll start solving the differential equation, and our temperature may go above 2000, and again our differential equation would blow up. So this initial guess is very, very important, the range we choose in. So I'm going to provide that initial range to you so that we don't have this blow up. But on a real problem, you will have to make a good estimate. Okay, so here is our problem. Our second derivative is a function of these three variables in principle, even though on the right hand side you can see only one variable is there, t. We don't have any x, we don't have any dt dx, but we are going to program it as if it is a function of three variables. Our boundary conditions on the left is t0 is 2000. We are going to guess dt dx at x is equal to 0 and try to match dt dx at x is equal to L is equal to 0. So actually I misspoke. At x is equal to L, t is not 0, but dt dx is 0. The gradient is 0. So the slope is 0. Sorry about that. Okay, so our length of the fin is 0.25 feet. We are going to use an h of 0.01 feet. Now I have chosen this just so that it is convenient to me on a spreadsheet. But you know that you would want to choose H appropriately so that it guarantees you certain number of decimal digits or significant digits in these temperatures. So you should definitely, in real life, you should run this solution for two different H values and then do Richardson extrapolation to find out how many decimal digits can you guarantee in your temperatures. So remember this. I am just showing you how you can solve a boundary value problem using methods that you have learned earlier. So we are going to use Runge-Kutta method to solve the initial value problem. And then we are going to use secant method to generate the series of guesses after the first two guesses. Okay. So let me fire up my spreadsheet. So here is my spreadsheet. And remember, so this is our big constant K. Remember, that's all of the constants combined. This is our length. This is our spacing. And this is our boundary condition that we want to match. Remember, it is dt dx, not t is equal to 0, but dt dx is equal to 0. And let's say for convergence, I want 5 correct decimal digits. Okay. All right. Now we need 3 functions in our VBA module. The first function is implementing Runge-Kutta method. So remember, we solve Runge-Kutta method. We have the 4 area estimates, K1, K2, K3, K4. And we are going to get a new X, a new Y, and a new Y prime. So this is going to return a vector of size 3. Okay. I don't know why there's a 4 here. It should be 3. Then we have our function x, temperature, and dt dx. We are going to import k from our worksheet named fin, cell value, range named k, and its value. And our function is very simple, k times t to the power 4. Okay. This is our secant function, so we are going to provide a guess target, first one, second guess, second target, and the value we want to match, and it will give us our new guess. Okay, so let's see. I should have, so developer tab, Visual Basic, and as I said, this should be 3. I don't know why I have it as 4. I just need these 3. Okay, so let's save that. Okay, so let's set up our spreadsheet. We'll start with our names. So we'll name this K. This is our L. This is our H. This is our match. And this is how many CDDs we want. Okay. All right, let's start our initial condition at x is equal to 0. T is 2000. And here is what I want to tell you about the initial guess. Now, our initial guess, we know that dt dx needs to be negative, but it needs to be around negative 16,000 or negative 17,000. If it is not, our solution is going to fail. So next thing we want to do is copy D11, which is our first guess, into C11, which is this one. So we copy and paste here, right? And we paste value only. So what I'm trying to do here is basically simulate. Each time we are going to generate a new guess, we are going to copy here. Okay, copy here, value only. Okay, now we are ready to solve our differential equation. So we are going to type our formula equal to Ranga, pass H, previous X, previous T, and previous T prime. Remember, we are calculating row vector, so Control, Shift, Enter. And then we are going to copy this down to row number 36. So we have our, at x is equal to 0.25, this is our temperature, this is our temperature gradient. Remember, this value is the one we want to match to 0. So let's bold this and box it. Okay. So we have solved the differential equation and we got an answer. So we are going to copy C36 and paste value only into E11. So this is the target we got, right? So before I do that, I don't want to keep scrolling back and forth. So what I'm going to do is I am going to hide certain rows. Let's say we hide all these rows. Right click, row, hide. So what this does is it allows me to see this entire screen. Okay. So this is our value we got, result. So we copy, paste special here, value only. And then we decide whether we have converged or not. So we say if absolute of this value minus match is less than equal to 0.5 times 10 to the power minus CDD. So we have not converged. So now we need another guess. So let's say our another guess is 17,000 negative because we shot high. So now we are going to lower our gun slope further. So copy value only here. So now this time we shot low. We want 0, but we got negative. But we are going to copy, paste here, value only, and we have not converged. We can see that. Now that we have two guesses and two targets, now we can use secant method to get our next value. So we say equal to secant guess 1, target 1, guess 2, target 2, and send match. So this is our next guess value. So copy, paste here. To target, shooting better. Copy, paste here. Still not converged. So we get a new guess. Copy this formula. Next. And this is our new guess. Copy, make this our initial condition. And this is our target value. So this time we shot up. Have we converged? No. So generate a new guess. So all I'm doing is keeping a record here. I don't need to, but it's good to see how we are converging. So you can see we are getting close to 0. What did I do? So we got to 1. Let's do one more iteration. We got 2 digits. New guess. And hey, finally we have converged. So this is our solution. So I'm providing you first few values. Okay. So you had values when the guess was minus 16,000. So you can check your spreadsheet. And then another spreadsheet when you have the third guess here. Okay. So this is my final true value, which seems different. Why is it different? Well, we'll figure it out. I don't know which particular iteration this was, but this is what I'm getting right now. And now let's plot X versus temperature. So let's magnify this, insert. We want just a smooth curve. Let's take it to a new sheet so that we can format it. First of all, let's select the data and make sure that we plot all data. Okay. Then let's say this we want to go up to only 0.25. And we definitely want 2 digits. Okay, this looks all right. And let's add our chart elements. So this is temperature profile. X-axis, horizontal, X in feet. Vertical, temperature in degrees Rankine. And we can move this chart back. Okay, so let's stick it kind of in the bottom here. And let's also unhide our rows. So we can stick it in here. Okay, let's format our sheets. So file, print. Let's do a page setup. We want grid lines, row column headings. Everything seems to be fitting there. Okay, folks, so we are pretty much done. Here is the grading rubric. Make sure that you have the right number of decimal digits, etc. And submit the lab report. Okay, take care.